Hi, I'm Mark Weitzman, and welcome back to Quantum Field Theory, a Student's Perspective. I'd like to start by once again thanking Martin, who put me on to OBS, which is Open Broadcasting Software, and he's given me some help. And so I think the appearance of these videos will be a lot better now. And this is the second tutorial on Lorenz transformations and special relativity. And so today we're going to do, we're going to try and do general velocity. I'm going to try and do general boost or velocity transformations. And we're going to do them in a general direction. And I also want to cover, so that's sort of like the main thing I want to cover. The next main thing I want to cover is a general factor theorem for how we can factor Lorenz transformations. And when I say Lorenz transformations in this lesson, I mean the restricted group. So that involves proper, the determinant of lambda equals 1, and what I call orthochronous, which is that lambda 0, 0 is greater than or equal to 1. So I won't always say proper or orthochronous, but the usual Lorenz transformations. We're not dealing with parity or time reversal. Okay. Now, so we're going to start by building up Lorenz transformations from the infinitesimal. And you've all seen how this goes, but just to review, let's say we're doing rotations in 2 dimensions. It's always good to go back to the easy cases. And then, so instead of a rotation by theta, let's do a rotation by theta over n times, and then take the limit as n goes to infinity. So most of the time today I'll be working with active rotations. So let's say this is an x-axis and this is the y-axis. And we have a point here, and basically an infinitesimal rotation rotates it a little bit. So it goes from here to here. And this is an active rotation. I'm actually moving I'm keeping one coordinate system, but I'm moving the system or the particle or whatever. So you can look at this diagram, and it's not too hard geometrically to figure out that x goes to x minus theta over n y, and y goes to theta over n x plus y. Okay, or if you want to write it in terms of vectors, we would say r goes to 1 minus theta over n r. But we're only doing 2 dimensions here, so we don't need any fancy. So what we want to evaluate and I know all of you have done this many times, but just in case someone hasn't. So remember, I is the identity matrix. So I've just sort of I left the 1 out here. I just split this up into the identity plus that. And you remember from calculus your basic exponential formula. So this is equal to e to the theta times this matrix, 0, minus 1, 1, 0. And the usual rule for evaluating e to a matrix is to use our basic formula. No different than regular calculus. Now, the trick is always that you find that this particular matrix, if you square it, it's going to be the, minus the identity or whatever it is. There's always a relationship. I'm not going to do these by hand here. It's probably faster to do by hand, but I do want to show you a little bit of how one can use software to do these things. As I said, this is a case where software will be harder, and doing by hand is probably faster. But let's do it a little bit by software. Okay, so this is a Maple worksheet, and since I'm going to be working with matrices and matrix exponentials, that's nice. What did I do wrong there? Gebra. This is why software takes longer than by hand. Okay. For those who haven't used Maple, the colon suppresses output. If I didn't suppress the output, you get all the possible commands in Maple, but we don't need to see that for now. And then I'm going to define a rotation matrix. Again, for those who are new to, so I'm going to do a 2 by 2 rotation matrix. I'm going to insert 0 values. And so our matrix over there was 0, minus 1, and 1. You don't have to put the semicolon, it will know automatically. And now we can just, if we want to do the matrix exponential, I can go matrix exponential theta times j, and there it is, and that's exactly what we expect for an active rotation. There's always a chance I get this sign right. It's 50-50. So that does the rotations. The reason why this works, by the way, is that theta is an additive parameter. In 2 dimensions, if I rotate by, let's say, theta 1, and then I rotate by theta 1 again, it's the same thing as rotating by 2 theta 1. So it's very easy to identify the parameter here with the end result parameter. So this is a rotation by theta. This may seem trivial and obvious, but when we do boost, now I'm going to do boost, and you'll see why this comes back. So let's do boost now. And as again, we'll use an additive parameter. which I'm going to call eta, which is the rapidity parameter that we discussed in the last tutorial. So under an infinitesimal transformation, we find t goes to t plus eta over n times x, and x goes to eta over n times t plus x. And so this is our infinitesimal transformation, and this is basically means that our matrix this time is just 0, 1, 1, 0. And instead of using theta, we're using this eta as the rapidity parameter. So we're going to have to exponentiate e to the eta 0, 1, 1, 0, following the same exact steps as we did last time. And again, this particular matrix has the nice property it squares to 1. So this is very easy to evaluate. And I'm going to go back to the Maple worksheet, and we'll define a boost, an infinitesimal boost generator or matrix. And this time it's 0, 1, 1, 0. And that sign, of course, makes all the difference in the world. And now let's do the same thing. Just going to eta asterisk. Okay. And see what we get there. Okay. So this doesn't look exactly like what we want. And when you use software, oftentimes you have to massage things into what you want. In this case, what I want to do is I want to convert every element of this matrix to a trig. And by trig, it also means hyperbolic trig. Percentage means the last evaluated thing. And okay, so that's exactly what we wanted. This is a Lorenz transformation. Remember that these gauches, hyperbolic cosines and sines are related by the velocity is equal to the hyperbolic tangent of the rapidity parameter. So this is good. Okay. Just to make that clear, that using v equal hyperbolic tangent of eta and hyperbolic cosine of eta is equal to gamma. Hyperbolic sine of eta is equal to gamma v. So our matrix, our boost matrix, becomes gamma, gamma, gamma v, and gamma v. And that's what we expect. So for one dimension, when we boost in one dimension, everything is fairly easy. Now, I want to do a general direction. I assume most of you have seen these, but not everybody. Depends on how good your background is in special relativity. Okay, so we have the boost matrices, which is the same as this. We're generalizing it. Here, remember, this is like time, and then this is x, only now we're going to have a y and a z. So we're going to have, let's call a spin matrix or a boost matrix. This is vector, not spin 1/2. Czernicki calls it S01 in one of the problems that we'll get to. This is equal to 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And I'm going to do this directly on the maple and save some time here. So let's define S01, colon. Now we have a 4x4 matrix. And we want this to be a 1. And we want this to be a 1. And I want to suppress the output. And I want S02, this is the Y matrix. Now we put the 1 in the Y row and column. And now we put the 1 in the Z. Oops. Okay. And now I want to, what we're going to be doing is our spin S, the spin, the total spin S is going to be the vector n dot the let's see, what notation did I use? I want n dot s. Get rid of that for now. So n dot s this is going to be equal to n is a has nothing to do with the rapidity, it's just the direction of the velocity, but it's a unit vector. So I'm going to do it as nx sx plus ny sy plus nz sc. And we have n as a unit vector. So that implies nx squared plus ny squared plus nz squared equal 1. And we're boosting, we're doing an infinitesimal boost. Boost in the n direction. So let us, I'm going to need this later on for some simplification. So side relation 1 colon equal okay. And so let's define just S, the matrix S. That's going to be nx asterisk s. I use 0, 1 there. Okay. To evaluate, so we're going to end up needing, just as we did before, we're going to need the exponential e, the rapidity parameter, times this matrix S. Okay. So we've defined S. Okay. That's what we expect. And to evaluate, I didn't show that. That's I didn't set this up as well as I should have. Okay, so that's our matrix S. And evaluating the exponential, we need to, it's a little bit harder than we usually have because we're working in 4 dimensions. But what you want to just show is that S wedge 3 minus S, and you want to show that this is 0. In other words, that S cubed is equal to S. And you can show that by simplifying. Maple doesn't do automatic simplification like I think Mathematica does. I wish it did. But using this thing, that didn't do what I expected it to do. Let me just think. S cubed minus S should be 0. That seems like it's 0. Okay, I didn't. Okay, I don't want to simplify S. So let me go back here and assign. Just assign a matrix to this. Now I want to simplify A. This should be 0. This is why software takes longer than doing by hand. Okay, so that's what I wanted to show. Now I'm going to just evaluate a general boost. I'm going to use the rapidity parameter times S. Okay. So, as usual with software, oftentimes you get long expressions. Sometimes they can go on for 100 pages if you've done something wrong. In this case, we haven't done anything wrong, but it just needs to be simplified. So, let me just make sure I assign it to B. Okay. So the first thing we can do here is use that side relation. Okay, starting to look better. Now we have the same thing with the exponentials instead of the trig functions. So I'm going to use that map thing again. By the way, I'm by no means an expert on Maple. I'm sure there are many easier ways to do this, and I've deliberately avoided using the physics package for this because I didn't want to screw it up. Okay, so this is good. At least we have exponential functions, but we can do a little better. So I'm going to define another side relation. Now I want to get things in terms of the velocities and the gammas. Oh, I don't want delta, I want gamma. Where did my gamma go? Okay, so and now I'm going to simplify it again. Okay, so now it's starting to look good. As a matter of fact, this looks real good. It has these nx's in there, and I'm going to, remember the velocity and the vector n are the same directions. N is just a unit vector, so nx times v is just vx. I'm going to substitute. But what's weird here is this thing over here. It should be the same as this. It should be 1 plus gamma minus 1 nz squared. And if you work it out, you'll find it's the same. I haven't been able to figure out. It's a question of how it evaluates in what order with respect to the side relationships when I do the simplify. But manually I could see that this is correct, so I'm not going to worry about it. But that's the way computer algebra systems, they have some funny quirks here and there. So I'm going to do one more thing. I'm just going to substitute. Okay, and that does look like the correct answer. I'm not using the total width here. Let me. So now we'll display it as a matrix when it has enough room. And again, we have this funny thing here, but you can compare this. You can compare this to. For instance, let's look on the Wikipedia page for Lorenz transformations. They got a lot of things on here. It's not a bad page if you already understand them. Yeah, I want to do a lot of scrolling till I get to, here it is. Okay, so you can see this thing on BV, if you compare it, it's the same as ours except for the sign of the velocity is different because I'm doing an active transformation. And you can also look in Jackson Classical Electrodynamics, 2nd edition, page 541. He has the same matrix. As a matter of fact, I highly recommend chapters 11 and 12 of Jackson. He's got 2 chapters on special relativity and its application to electrodynamics and their problems. They're very good. And he goes into detail on things like the Thomas procession and on classical equations of spin in electromagnetic fields. So I do recommend you can do that. I want to do one more check. One thing you should try and verify is to make sure you have the right rapidity parameter. So let's check that eta is actually the rapidity parameter in this boost matrix. And the way we do it is, look at a particle. Imagine, let's say we have a particle at rest at the origin. So its coordinates in the original reference frame tau 0. Tau is the proper time. And that also equals coordinate time, since the particle is at rest. Now, if we want the new coordinates after we boost it, it's just a multiplication of the boost matrix times the vector, tau 0, 0, 0. Now this is very easy to evaluate. If we go back to the Maple thing, let's go back to the Maple worksheet. Imagine multiplying this matrix by a vector which just has a tau, a 0, 0, and a 0. Everything here, these three things always hit the 0, so it's just this column here, basically. So what we're going to get is, well, I'm actually using the form of the matrix before I'm sort of using this form before I want to keep the rapidity parameters. So anyway, this is equal to, when you do that multiplication, it's just the first column. So it's tau gauche eta nx tau sinh eta. I probably should have done it with the second form, but it doesn't really matter. And y tau hyperbolic sine of eta, and nz tau hyperbolic sine of eta. Now, the velocity, the new velocity, not the 4 velocity, but in the new reference frame, the new velocity is defined as the coordinate x prime I divided by x prime 0. In other words, the particle, when you have a particle moving along this world line, this is its time coordinate, these are its spatial coordinates, and velocity is distance over time. Nothing fancy here. So this is just equal to ni, the component of n, tau sinh eta divided by tau gauche eta, which is equal to ni hyperbolic tangent of eta. And this is what we want because, if we would ask what the velocity is, we would square all three components, and then we'd have the normal vector, which squares to 1. So v ends up being equal to hyperbolic tangent of eta. And that's exactly the relationship between velocity and rapidity parameter that we want. Okay. Now, if we go back to the Wikipedia article, we can see, if I can find it here, that they have another definition of a general Lorenz transformation right here, these two things. Let's look at this one over here on Lorenz Boost. This is a very simple formula, and So using active instead of passive, we can write a general Lorenz transformation as and now you can also find this in Jackson, page 517. Whenever I cite Jackson in this course, it's always the second edition, which is the edition that I owned before he went to MKS units. Big mistake. But you can also derive this, using, if you're careful and you do it correctly, parallel and perpendicular components. That is, you use the usual Lorenz equations for one dimension. I spelled that wrong. And you can get that as well. And on my Maple worksheet, we can verify that. We can go the Boost matrix times. Now let's enter a 4 by 1 a column vector. I'll just put T, X, Y, Z, and you can verify. Let's just do the T one because that's the easy one. So we should have gamma T, which is what we have, and then we have N times V is just that component. So we should have VZ, gamma Z, VY, gamma Y, VY. And if you look at the, if you pause the video and you look at the other three things, you'll see that they're equal to what we found on the Wikipedia page and in Jackson. So let's go back. That sort of does the general Lorenz transformations. And now I want to do this factor theorem. I don't think that it has a name or anything, but it's an important theorem. And it basically says every Lorenz transformation, and remember, I'm only considering proper orthochronous or restricted Lorenz transformations, can be written uniquely as a product of a rotation and a boost. So if we have a Lorenz transformation lambda, what the theorem says is we can write it as B times R. This would mean we would rotate and then we would boost. Or we could write it as, what happened there? We could write it as a different rotation and a different boost. Now I'm only going to show, I'm going to show this part, and I'm not going to show the uniqueness. Showing this part this way is very similar, and the uniqueness is not hard to show. So what we're given is we're given a restricted Lorenz transformation, and I need to show it. I can factor it like that. So let's start by defining the velocity I'll use upper indices, but it doesn't really matter. So this is just, we have the matrix. You have a matrix. You have all the components of the matrix. So you can certainly define this thing. Whether it's really a velocity or not, we need to show. Now, in the lecture on Lorenz transformations, we showed that for restricted Lorenz transformations, lambda 0, 0, 0 squared minus lambda I 0, lambda I 0. Now, remember we're using the summation convention, so this is equal to 1. Now, if you divide this equation by lambda 0, 0 squared, and remember that lambda 0, 0 is greater than or equal to 1, because that's what the restricted have, we immediately will get that 0 is less than or equal to v squared, which is less than 1. So this shows that it's a legitimate velocity. We're not having velocities greater than light here. So I want to start by, let's calculate some things like B. B is the boost matrix that we calculated earlier in the lecture. And I want to look at the 0, 0 component. And if we go back to that maple sheet, you can see it's gamma 0, 0. So we know this is gamma. The fact that we're taking the velocity opposite doesn't affect gamma, so that doesn't matter. Remember, the definition of gamma is 1 over the square root of 1 minus v squared. And this is going to be equal to 1 over the square root 1 minus lambda r0, lambda r0, lambda 0, 0 squared. This becomes algebraically equal to lambda 0, 0. So I'm just showing everything works out as we would expect. And since this is equal to 1, it's just lambda 0, 0. So what we've shown is that the lambda 0, 0 component is just going to be equal to gamma in terms of the velocities when we define the velocities this way. So now let's calculate some other values of a boost. And none of this is obvious. I'm just copying a proof that was in one of my books. So B minus V 0R. Okay, so what is that equal to? Let's go back to the Maple worksheet. Remember, 0 is the row and R is the column, so it's gamma times the velocity component in that direction. Except that we're using a negative velocity here, so all of these we should make negative. So this is equal to minus gamma VR, which is equal to minus gamma lambda R0 over lambda 0, 0 by the definition of VR. And then we've shown that gamma is lambda 0, 0, so it's minus lambda 0, 0 over lambda 0, 0, lambda R0 is equal to minus lambda R0. Okay. So we have these two things. Now let's define a new Lorenz transformation. R equal B minus v times lambda. Now, the key thing here is that this is a Lorenz transformation. Lambda is a restricted Lorenz transformation, and all boosts are restricted Lorenz transformations. And as I stated, I might not have proved it, but it's something that's not difficult to prove. The restricted Lorenz transformations form a group. So the product of two elements of the group is another element of the group, so R is a restricted Lorenz transformation. So doesn't do what I want. So R is a restricted Lorenz transformation. Okay. Good. Now let's calculate R00. Well, it's just matrix multiplication. So I have B minus V, 0 mu, lambda mu 0. And here, mu goes from 0 to 4. So this is just B minus V, 0, 0, lambda 0, 0, plus B minus V, 0I, lambda I 0, where we're summing on i's. When we sum on Latin indices, it's a spatial summation from 1 to 3. Okay. So this is equal to, we already established earlier that B minus V 0, 0 is gamma, and that gamma is lambda 0, 0. So this is equal to lambda 0, 0 squared minus, and we also established that B minus V 0 R or I is minus lambda R 0. So this is equal to minus lambda I 0, lambda I 0. And if you remember our identity, it's right over here. This is equal to 1. So now we have real good things. Because what we've established is that R00 is 1. This implies, and I'll explain why shortly, that R is a rotation. Because let's just draw our lambda, not our lambda. What we've shown is that there's a 1 here. Now, if there's a 1 here, there has to be zeros here and zeros here. Because of this basic identity, that lambda 0, 0 squared plus, if lambda 0, 0 squared is 1, it means that lambda I 0 times lambda I 0 is equal to 0. So all of these rows are 0. I didn't show it explicitly, but when we used our basic elements, when we derived this formula here, if we had used n mu nu instead of n mu nu, we would have gotten lambda 0, 0 squared minus lambda 0I, lambda 0I. Okay. This one is lambda I 0 gives us this one over here. And then this identity, which is the same thing with lowered, gives us the other row. Anyway, you can work that out. So what we have here is we have, remember, this is the time. First row over here is time. First column over here is time. And everything else is spatial. And what we have is a big orthogonal, this is a big O, big orthogonal transformation. It's a special. With determinant 1. Because the determinant of this matrix is just going to be 1 times the determinant of this. We've already said that the Lorenz transformation has determinant 1 because it's restricted. So this is just an orthogonal transformation with determinant 1 or a rotation. I haven't put in every detail on this, but it's pretty obvious. So we've established that R is a rotation. Now we can write lambda. We're right at the end of the proof. We can write lambda as BV times B minus V, because this is the identity matrix. Times lambda. It should be very obvious. You could actually multiply these boost matrices by themselves, but it should be obvious that if you boost in one direction and then you boost in the opposite direction, you come back to where you started. It's just the identity. So now this is equal to, we have B times V. And we defined B minus V times lambda as R. Remember, we always have associativity. Whenever we have a group, we always have associativity. So this over here is equal to R. And that's our proof. Because B is a boost. And we just showed that R is a rotation. Okay. Now I want to end this. I know this has gone on for a long time. I just want to end this by discussing two things. I won't calculate anything, but I'll just something every student of physics should know. And the Thomas procession. If you recall from the Lorenz transformation lecture, that the boost generators don't commute. Ki, Kj is equal to minus I, Ijk, Jk. Forgetting about the minus sign for now, what does this mean? It sort of tells me that if we do two boosts in a row and then do them in the opposite direction, we're going to get something that, remember, J is the generators for a rotation, so we're going to get a rotation. So two consecutive boosts in different directions is not a boost. So if you boost in this direction and then you boost in this direction, it's not a boost in this direction. Wrong. It's a boost plus a rotation. And so this leads to the Thomas procession, which is important in understanding spin-orbit coupling in the hydrogen atom when you do a perturbation treatment. If you start with a relativistic treatment like with the Dirac equation, and I think Barton Zybeck might do that, he switched, then you don't have to worry about this Thomas procession. But if you're going to just use the Schrodinger equation and you're going to use perturbation theory and you're going to put in some things by hand like spin-orbit coupling, this is where it's most useful. Then you're going to need to take into account that two boosts in different direction leads to a rotation. And the QM books show that there is a factor of 2, which for a while early in the 1920s wasn't well understood. But it turns out to be a special relativistic effect. It's treated very well and in a lot of detail by Jackson. In section 11.8 of the second edition. And it's treated elsewhere as well. And I'll just give a hand-raising argument, just a classical argument. Imagine you have a proton and you have an electron, which is orbiting a proton. What we usually do to understand the interaction is we say, let's go to the frame where the electron is at rest. To do this, let's say this is a x, y. So at this particular spot, we boost in a y direction. But in this frame, the electron, it's at rest, but it's still going to feel a Coulomb force. It feels, in this frame, there's both an electric field and a magnetic field. And we use the usual, like, these factors aren't right, but we use things like G mu, B dot S to get the interaction energy in this frame, the spin-orbit coupling. Now, the problem is that the electron also feels a static, even though it's at rest, it feels an electrostatic attraction to the proton still. So it's going to accelerate in the minus x direction. So that's going to lead to a change in velocity in the minus x direction. And in order to keep it at rest, we have to boost in the minus x direction. So we end up with 2 boosts, one in the y and the other in the x, minus x direction. As I just explained earlier, when we have 2 boosts in different direction, this leads to a rotation. So in the electron rest frame, or what you call the electron rest frame, and Jackson does this in more precise detail, I don't know why that happens. I'm going to have to learn how to use this software. The electron is rotating. Well, the frame is rotating. So we get an additional spin interaction. And that leads to a factor of 2. It's not exactly a factor of 2, but in the non-relativistic limit it is a factor of 2. Okay, so that's all I want to say about the Thomas procession. And then finally I want to add one thing. I'm not going to show any calculations here, but you have to be very cautious in special relativity. You don't want to use the word see. See implies you're looking at it with your eyes. And what you really want to use is the word observe. Because an observation takes into account everything. So for instance, if something's a mile away from me and it explodes, and 5 seconds later I hear the sound, I'm going to say that I heard the explosion, even though I actually heard the explosion 5 seconds after it happened, because sound takes 5 seconds to travel a mile. The same thing happens with light. When we see things, we're not seeing things exactly as they are at the time in the reference frame, because we have to take into account that it's a distance away and light travels at a velocity c. So we have to, take this into account. Penrose was the first one to observe, I think in the early 50s. And I'm not saying he was the first or the only one, but he's certainly the most famous one who made this observation, that when we correct what we see, discovered or pointed out that even though objects may be Lorenz contracted, and this is a real physical effect, they may not look that way. We might not see them that way. And what Penrose showed, just as an example, is that all spherical objects look spherical in any Lorenz reference frame. I'm assuming that the sphere of the ball is either at rest in some reference frame or traveling at uniform velocity. So you might think that, let's say here's a ball in my reference frame where it's at rest, and that's my best attempt to draw a circle. I'll see it as a circle. You might think in a reference frame moving at a velocity v that it would contract and might look like this, it would look like an ellipse. But that's not true. That's not what we see. That's what happens. It still looks like a ball. Sorry. But it actually is rotated a little bit, but it still looks like a sphere. And all I can say is if you want more information on this and you want to prove this to yourself, see Rindler's book on special relativity and cosmology, section. Has some interesting mathematics on conformal transformations. So with that, I'm going to end this lecture. Next lecture, we're going to do problems from Schnecke's book, and then it will be on to canonical. That's definitely not spelled right. I'm not going to even spell it. On to a canonical quantization of scalar fields. So thank you for watching, and again, I appreciate feedback both on the content and on the form, and I recommend visiting my Piazza site to leave that feedback. You could also leave it on the YouTube site. I'll see you next time. Bye-bye.